All right, so in this video, we are going to be comparing linear and exponential functions. Which one is better odds of working with money or populations, and some real life scenarios like our half-life formulas. All right, so from a question, just try to remember what arithmetic and geometric are. So if I'm talking about an arithmetic sequence, an example looks like this. So how do I get from 2 to 4, 4 to 6, 6 to 8, 8 to 10? I add or subtract. Okay. So arithmetic thinking adding, right? So I'm adding or subtracting something. So then I got to think, is that linear, exponential, or quadratic? Right? This is going to be linear. So remember, linear is my y equals mx plus b. Sorry, that equal sign got weird. B is the y-intercept. M is where you're moving. So that rate that you're moving up by. Okay? Or you might see it as my arithmetic sequence with an a sub 1 in it. Okay, our next one is geometric sequences. So I've got an example right here. So how do I get from 2 to 4, 4 to 8, 8 to 16, 16 to 32? I'm multiplying through each term. We are not going to say divide. Okay, because when we're talking about multiplying, we're finding a rate of something. You don't say, when we're doing this into our actual geometric equation, you don't say divide by half, or divide by 2. You say multiply times a half. Okay, so his little geometric sequence looks like this. So this is what we're going to talk about, and then we're going to compare him to an exponential equation. Okay, so thinking back to this, what do all the variables in it mean? So if I say a sub 1, what does a sub 1 mean? Okay, a sub 1 is going to represent my first term. Okay, my r then is going to be the rate that I multiply by. My n is going to be what we call the term number. Okay, so am I talking about finding the 15th term? Do I want to find the 10th week? Okay, that's what those n's are going to kind of mean. Rate is what we multiply by. So if you kind of think about it when we're doing our exponential equations, the rate will still be the exact same. It is what you're multiplying by. It also tells you whether you're increasing or decreasing. So if I multiply times 2, I should be getting bigger, increase. If I multiply times a half, I will be getting smaller, decrease. Okay, we're going to go ahead and skip this product rule of powers. Okay, what we're going to do today is construct an exponential function from a geometric sequence and work them back and forth. So we're going to look at a geometric sequence and the exponential equation and see how they work together. We're going to be talking about whether they're growing or decaying. We're going to be looking at it based on tables, graphs, different equations and different scenarios, and then we're going to compare them to linear functions. Okay, so when you work with sequences, you often use something called repeated reasoning. This means that you notice when a pattern repeats and think about it, how a pattern will extend when repeated. All right, so this warm up here, we're only going to do this first part of it, and then we're just going to kind of talk about it. So there's a couple videos on this. There's a Mythbusters video where you actually fold paper. So the myth is you can only technically fold the paper in half. So if you fold it in half, fold that in half, fold that then in half, and you keep folding that paper in half, you can only technically fold it 7 times. The max amount, any size paper, you can fold 7 times. Mythbusters take it and they do this gigantic one that's probably like a football field long, and they keep folding it, and they do get it past 7 times, so they break that myth. So there's an example of one here. If I have this box and I want to cut it in half and keep cutting it in half, so there I'm cutting it in half. There's my first split. Then I'm going to take one of those boxes and I'm going to cut it in half again. I'm going to take one of those boxes, cut it in half again. I want you to pause the video and just keep that pattern going and see what happens to my shapes. Do they get bigger or do they get smaller? Okay, so what you should notice is that you just keep getting smaller. Keep getting smaller until you can't really do much anymore. All right, this means it's a decreasing. We're multiplying times a half each time. So that rate that we're going by is a half. We are getting smaller and smaller and smaller. Okay, so this is an exponential function because we are really big and we get small very, very quickly when we're multiplying it times a half. All right, so let's go into an actual example here. It says Allison and Beth each receive $10 per week for doing chores for their neighbor. One day, Allison decides to increase her income using her knowledge of exponential growth. She proposes that her payment change to a penny for the first week and then double each week thereafter. So in week 1, Allison is having a penny that she will add Beth will add $10. So in week 2, how much will Allison be adding? She should be adding 0.02. Well, Beth will still be adding 10. Okay, so what I want you to do is pause the video, and I want you to try to keep this pattern going and see what you notice. All right, so that should be what it looks like. I'm going to go ahead and flip to the next screen here. There you go. Okay, so in question 2, how does Allison's income change as the number of weeks increase? What are we doing each time? We are multiplying by 2. Okay, does Allison's income represent an arithmetic or geometric sequence? Allison's, we're multiplying by 2, so she is a geometric sequence. Remember, multiplying term to term. Okay, write an equation to represent Allison's income GMN after n weeks. Okay, ignore this down here, that means the same thing. Okay, so I kind of talked about it before. There's my geometric sequence. So a sub 1 stands for the very first term. So my very first term, this is kind of like my x value. So my first term for Allison is 1 cent. So G sub n is equal to 0.01. R is the rate we are going by. So what did I multiply by? I multiplied by 2. And it's to the n minus 1. So eventually we're going to translate this into like an actual exponential function and see how they correlate to each other. And what is the value of g of n when n is 0? So here is my equation again. It says plug n is equal to 0. 0.012 to the 0 minus 1. So does this value make sense in the problem situation? So go ahead and plug this into your calculator. And G sub 0, you should get half a cent. Does it make sense? Well, first off, what does the 0 mean? When I say G sub 0, and I'm talking about those n's, what does n mean? So if you think about it, this is kind of like when I referred to the warm-up, the x's. I just put g of x, okay? You could have it representing x if we're trying to actually graph it into a graphing calculator. So then what does the x actually mean? Well, back here I put x as my number of weeks. So if I go back, this is basically saying at week 0, I should have half a penny. Which means at week 0, that's how much money I would have in my bank account before I even started my job that they're trying to do. In my scenario, did I say anything about having any money into my bank account before I even started my chores? No. So I shouldn't have half a penny starting in my bank account at week 0 because I haven't even started my jobs yet. In week 1 was where I made my first penny or my $10 in terms of that. Okay, so this scenario is not going to work because at time 0, I'm not starting with half a penny. Okay, if the pattern were to continue, how many weeks would it take for Allison to have a greater weekly income than Beth? So what we're going to do is we're going to graph this. So my first one we're going to graph is my 0.01 times 2. We're going to use an x. Okay, and the other one is a constant 10. So we're just going to put the first one in y1, the second one in y2. If you have a TI-83 or an older TI-84, remember, if you're doing your exponent, you have got to put the x minus 1 in parentheses. So when you type it in, you'll do your caret, and you'll do this. If you get prompted with the actual power, you can just type x minus 1. Always fails, put parentheses. You'll always be right. Okay, so I'm going to pause this real quick and throw it on my graph. So go ahead and get on your graph. We probably have to adjust our windows. All right, so I'm going to show you guys what my y equals looks like. So it looks like that. And my graph looks like this. I can't really see anything. So I need to adjust my height of my y-axis and how far out my x-axis goes. So when I go to my window and adjust this, we're going to put 20. And for my y-max, I'm also going to put 20. All right, so it says, back to this question, okay, at what point would it take for Allison to have a greater weekly income than Beth? So what we're going to do is we're going to find where they intersect first. And then after that intersection, I know that she's going to take over Beth. So I'm going to press second, trace, intersect, and find out when they're the same. I'm going to use my left and right arrows to get over there. And I'm going to press enter 3 times because it's going to go through my first curve, which is my blue one on mine, my second curve, which is my red one, and then it's going to tell me to guess. Okay, so at 11, I should be overtaking Beth. So at 11 weeks, I should be going over. Okay, because at 10.96, that's when they're about the same. Okay, we're going to skip this for now. Okay, calculate the income that Allison would earn per week in each week given 15 weeks. So first off, my equation that we have been using is this. So I got to figure out, is that 15 going in for the X or for the Y? So which one represented the weeks? Okay, this X was my weeks. The Y is my money after that week. Okay, so what we're going to do is be plugging that 15 in for the X, or there is another way to do it. Let's say you don't feel like typing it in. Look at your table. If you look at your table value, so I'm going to press second graph. You're going to get all the way up to 15, so I'm going to actually cheat a little here. So I'm going to look at my table set, and it's set me to 15 here. Okay. If I scroll over, it will give me my exact amount of money on my 15th day, so $163.84. So this one we're going to get $163.84. Please make sure you get that change in there. So that means if you do one that's a little bit lower, so like this one here, make sure if you actually scroll over, it will give you that change. Okay, so go ahead and find the next two. So pause the video, find the next two, and then I'm going to state what the answers are. All right, so for the 20th week, you should be getting $5,242.88. For the 24th week, you should be getting $83,886.08. Okay, so the next thing that we're going to do is kind of just look at the graph of it. So it says, predict the shape, talk about some characteristics. So if I take off Beth's here, what are some things you noticed? I want you to pause the video. I want you to describe some things you noticed. Are there any numbers you can get out of it? Do you know anything about the graph? Okay, what does it kind of look like? So pause the video and try to write down as many characteristics as you think you can do. All right, so some characteristics that I noticed. It is an increasing function. We already knew that we were multiplying by 2 each time. Okay, so I know the rate is going up by 2. Another thing I want to do is I want you guys to find the y-intercept. So pause and try to think, how do I find the y-intercept? Kind of look at your calculator. Is there a way to do this? So I'm going to press my zoom standard so I can keep that in closer to that. Okay, how do I find where it's crossing my y-axis? So if I go back here, we know it's increasing. No, the rate is 2. Okay, if we think about what an actual y-intercept is, if I actually do this point here, that point is 0, 1. If I do this point here, that point is 0, 4. This point here, that point is 0, 1, 2, 3, 4, 5, 6. All of those x values are 0. So if I look where my x value is 0, if I plug 0 in for x, I should find my y-intercept. So if I go back here and look at my table, okay, my y-intercept is 0.005. Yep, which is what we found earlier. At time 0, it was 0.05, or half a cent. Okay, what I want you to do next is I want you guys to graph this equation in your calculator along with the other one that you have in there. So both of those at the same time and see what happens. They should be the exact same graph. So these are the exact same graph. They're just starting at different values. So one starts it at its y-intercept, the other one kind of starts it on its first term. That little -1 kind of means, hey, I started at my first term, not the original start. Okay, so what you learned in IM1 and IM2 is the one on the left. So the left is what we kind of practice when we do transformation. So A times B to the x, where this was my y-intercept, and this was the rate that I went up by. Okay, you get hammered with this in IM1, where you convert from the geometric back to your exponential. They're both exponential equations. The left one is an actual exponential, while the other one we call a geometric sequence that creates an exponential. Okay, so we're going to kind of delve into like how they are related to each other. Just realize they are the exact same equation. One just starts on my first term, the other one starts at time 0. All right, so Beth is amazing how quickly Allison was able to make a lot of money and decides that she wants in on the action. She adds her 2 friends, Quentin and Alicia, to help her come up with a plan. So Quentin, you could start with $1. Okay, so that's a big thing right there. We are starting with $1. So at time 0, Quentin starts with $1. Okay, so at week 0, Quentin's at $1. Alicia also starts with $1. Okay, and then she adds another $1 each week. So if I start with $1 and I add $1, I'm now at $2. If I add $1, I'm now at $3. If I add $1, I'm now at $4. I want you to continue that pattern. Okay, then Quentin is adding 50% more each week. So if I'm adding 50% more of this, I should be at what? $1.50. Okay, if I add 50% more from that, go ahead and try to type that in your calculator. Okay, you should be getting $2.25. All right, so the problem is I don't like to times it by 0.50 and then add it to it. So what we're going to do is we're going to find the rate that we're multiplying by each time and not having to do that add part. So yes, I'm multiplying going forward. So right now we have this. So I am multiplying going forwards. But if I want to take it backwards, because I don't really know what just a single multiply is without that adding, I could divide backwards. So I want you guys to take 225 divided by $1.50 in your calculator. The rate that you're multiplying by is 1.5. So take 225 times 1.5 and you'll get your number 3 answer. Then take that times 1.5, you'll get your next one. And continue that pattern. So go ahead and finish this out for me. All right, so here are my answers here. Okay, so the next thing I want to do is we're going to create some equations here. So first, if I'm looking at Quentin's equation, I multiply term to term, so it is a geometric sequence. So we could create that geometric equation. Okay. What I want us to start practicing is making the exponential equation from that. So the exponential equation, so let's get Quentin's name up here, was using the y-intercept, whereas the geometric equation was using the first term there. They both have the exact same rate. Okay, and then this one is just to the x power because we're starting at the actual starting point. Okay, ooh, that was in an N. This was an A and B, sorry. I use the correct letters. All right, so the y-intercept. Y-intercept is when the x value is 0. So when is the x value 0? Quentin's is 1. What is the rate we multiply by? 1.5. Right, so there is Quentin's equation we're going to graph, and then we have Alicia's. So Alicia, how do I get from 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6? We added 1. Okay, so my y equals mx plus b if I wanted to do it. B stands for the y-intercept. Okay, her y-intercept, so at times 0, she started at 1. The rate she moved by was a 1. Okay, so we're going to graph these because I'm going to show you guys how to change your window based on what the table is. So go ahead and get those into your graphing equation. Okay, once you have it in, what we're going to do is press window. So when you press your window, I'm going to look at the x values. So my smallest x value is 0. So my x min, I'm going to put at 0. My x max, I'm going to put a little bit bigger than 9. I'm going to put 10. So for x min, do 0, x max, do 10. For your y min, make it 0 again. Your y max, let's get all the way up there to 20. Okay, so you will be doing from 0 to 20. I want you to go ahead and graph that and put it up there. You should see that it is an increasing function again. I'm not going to put the graph up there, but the line and the exponential are a lot closer together. Okay, so remember, if you need to look at their table values to get this graph, press your second graph. You can look at those table values to be able to do it. Those aren't correct because I didn't actually put the right equation in. Okay, what I want you guys to do is figure out when will they be the same. So do your second trace intersect, and then give me a time period that Quentin will be above Alicia, and write that in. Okay, so you can compare with a classmate. Otherwise, I am going to continue on to our last lesson here, 1.3. So Simon is studying for a big test and is trying to stay awake. He drank a 12-ounce can of Big Buzz energy drink that contains 80 milligrams of caffeine. He is wondering how long the caffeine will stay in the system if the caffeine is a half-life of 5 hours. A half-life is the amount of time it takes a substance to decay to half its original amount. The term half-life does not just apply to radioactive material, it is also used in medicine to describe how long a chemical exists in the human body. Most of the time when you hear half-life, it does have to do with radioactive material. So like if I took a bunch of radioactive material and I put it in the dump, it is saying like how long, how many years will it take for it to decay. So what it does is it decays in the amount of time in half, hence the name half-life. So it will decay half of its amount in the amount of time that its half-life is given. So however many decades or however many years. Okay, so it's decaying in half by the amount of time, which is why it's called a half-life. So most of the time you hear about it as radioactive decay, so something sitting in a dump, how long it takes for it to actually go away. So how much caffeine remains in Simon's system after 5 hours? After 10 hours, explain your reasoning. So what did we originally start with? 80 milligrams. I guess I can put mg. Okay, so then if I go back to my scenario here, we did the 12 ounces, doesn't really matter to us. I talked about the 80 milligrams. Its half-life is 5 hours. So I cut it in half in 5 hours. So in 5 hours, what is the done going to be? It should be 40 milligrams. Okay. Then after 10 hours, so another 5, I should be at 20 milligrams. So then we're going to put this on this beautiful chart. So go ahead and fill out the caffeine in the system by the amount of hours. So pause the video and go ahead and plug that in. Okay, we should get this. The number of half-life cycles, we're going to kind of ignore a little bit. Basically, it's saying how many cycles did it go through. So it's going to go through 1 cycle, 2 cycles, 3, 4, 5. So on the 5th cycle, oh wait, sorry, 0. It didn't go through its cycle yet. So it hadn't cycled yet, but after the 1st cycle, we are now there. My 2nd cycle, 3rd cycle, and 4th cycle. So after the 4th cycle, we will have 5 milligrams of caffeine left in our system. What is the initial amount of caffeine in Simon's system? 80 milligrams. What's the rate that we're decaying by? We are cutting it in half, so I am doing it by 8th rate. So I'm going to put R equals 1/2. The rate that we're going by is a half. I'm cutting it in half. Notice I did not put divided by 2. Okay, we are multiplying times a half. All right, so Emily, Tyler, and Renee were asked to write an exponential function AT to represent the amount of caffeine remaining in Simon's system. So Emily's is correct. It is not supposed to have this weird little T behind it. Tyler and Renee are incorrect. So why is Tyler's reasoning incorrect? And why is Renee's reasoning incorrect? So I want you to pause the video, and I want you to look at what they said for Tyler and Renee. I want you to graph them and look at their graphs, see if you can get anything from that, and try to decide some reason on why both Tyler and Renee might be incorrect. So pause the video and go ahead and try that on your own. All right, so the issue with Tyler is you can't really have negative time. So when I plug that in, it's going to give me negative time. Okay. This function, if I actually look at it, it's up. So we are going to have 80 times, I'm going to use 0.5 caret. Notice you don't have to use parentheses unless you are a TI 83 or older 84. Okay, so I'm going to do negative x divided. There we go. And then I'm going to have to rezoom my window. I see a little blue dot in the top left. So if I redo this here, I'm going to change this to negative 40 and this to 40 because it looks like he was in my top left. There he is. Okay, I cannot have negative time. That graph gives me all negative answers, which is why his is not working. Okay, if I look at the other equation here, Renee's is a little bit harder. So she has my 80 times 1/2, and she decided to times by that 5. So she did x times 5. Okay, I'm gonna have to probably, we might be able to just rezoom. So I'm gonna do my zoom standard and see if I can see it. All right, so here we have my zoom standard. Okay, it looks like it flattens really quickly. It looks like it's almost hitting that 0. All right, the hard part about this one is we can't actually multiply times the 5. So when you're doing half-lives, you aren't doing it by hour. We're doing it generally in increments. So we have to divide by that 5 to break it up into those increments. Timesing by 5, it's actually making it larger. Okay, so we actually have to divide by the 5, which is why Emily's is the correct one, because when you work in half-life cycles, a cycle happens and then another cycle is completely different from it. So you kind of have to divvy it up between those cycles. Okay, so how much caffeine remains in Simon's system after 2 hours? So let's go ahead and take Emily's equation here. Okay, here's her equation. So what does the x mean? What does the y mean? So if I go back here to my table, what do we think the x represents? What do we think the y represents? Well, the x is my hours. The y is my magnesium left, or not my magnesium, my milligrams left in my system. Okay, so technically I'd be plugging that 2 hours in for the x. They're both in terms of hours. X divided by 5, that 5 is in terms of hours, so I don't really have to change anything. Or if it was in minutes, we'd have to be careful. Okay, well, let's say I don't really want to plug that 2 in. Let's look at our table. So I want you to look at your table where the x value is 2 and go ahead and figure out how much would be in my system. So go ahead and answer that next question. And then I want you to try to figure out number 6, where Kendra suggests that she can calculate the amount of caffeine remaining by rewriting the equation. A of t is equal 40 to the t divided by 5. See if that means the same thing, because we wrote an exponential that was similar and they looked like the same graphs. They started in different spots. So if I took my 80 times a half to get 40, does it mean the exact same thing? Can I take 80 times a half, get 40, and then have the same equation where when I plug that number in, it works? So go ahead and pause the video and try those 2 questions. All right, so you should have gotten 60.6 milligrams for question 5 when you looked at 2 hours. Okay, Kendra's, they are not the same graphs. If I plug 2 in or look at the 2 value for x, you are not getting the same answer. If I looked at both the graphs will not be the same. You cannot multiply things that are not the same base. I cannot take 80 times a half and get 40. It is not the same mathematically. It is a completely different graph. Okay, so keep those bases unless they're the same. So they don't mean the same thing. So now we're going to go to the next page here. Okay, question 7, it says, use technology to predict when the caffeine will be completely out of Simon's system. So pause the video. I want you to try to answer 7 and 8. All right, so if I look at 7, I want to know when I have 0 milligrams. If I keep going, I will never hit 0. What you should remember is graphing exponential equations, they have asymptotes right here. You technically will never be at 0 because exponentials have asymptotes. That asymptote will move up and down if the graph shifts up and down, but otherwise it will always be at y equals 0. So technically, you will never actually have 0 milligrams in your system. You might have 0.0000001, but you'll never be at 0 because of the asymptote. So that should answer your question 7. Question 8. Approximately when will the amounts of caffeine remaining in time and system be less than 1? So go ahead and look at your table again. Okay, it's around between 31 and 32 hours that you guys should be getting close to being under 1. Okay, question 9 here. Use the properties of exponents to rewrite your function so that the only variable t is the exponent. So right now we have, well, that's a t. I'm going to keep it an x to make it easier. We have this. So I need to figure out how can I rewrite this where that divided by 5 isn't in there. So there's actually a way where we can write another type of equation. That's still the same exponential, but maybe the base or the y-intercept is a little bit different. Okay, but it is the exact same function. So it says what percentage of caffeine will remain after each hour. So it's how do I figure out how to translate this equation? So what we're actually going to do is we're going to do an exponential regression. So if I go back to my table, it was kind of x, y, 0, 5, 10, 15, 20. Wait, or did I do that backwards? Nope, that was it. Okay. So then I had 80, 40, 20, 10, 5. So this is going to be my L1 and my L2. So now I got to think, ooh, how do I do another exponential regression line where it's just going to give me my general y is equal to a times b to the x. So think about it. How do you get that exponential regression line? Okay, what we need to do is go to our stat button, edit. I'm going to go up and clear all this out. Type it in, so I got 0, 5, 10, 15, 20. Then I got 80, 40, 20, 10, 5. Then I'm going to go to my step. I'm going to calculate. I'm going to go to number 0 here where it's exponential regression. And I'm going to calculate it. So there's my a. Remember that caret means to the x power. So I'm going to fill in my a. So it's y equals 80. Notice it's got the same y-intercept, but the rate kind of did that division of 5 kind of in it. So 0.87 to the x. So it says what percentage of caffeine will remain after each hour. So it's like basically taking that 5 and doing it per hour now. Okay, so 87% of caffeine will remain after every hour. Okay, so then I'm going to look at one more question in here where it deals with how does the half-life after 8 hours rather than 5 hours affect the amount of caffeine remaining in the system? So if I go back to my original here, there's my 5-hour one. What do I have to do to make it to where I compare it to the 8-hour? So I need to replace that with an 8. Okay, go ahead and compare them. Look at their tables, look at their graphs. What do you guys notice when you're looking at them to decide when I make that time period longer, what happens? Okay, what you should notice is when I make my time period longer, so my red one, my 8 years, it takes a lot longer for it to decay. So when you are doing your time period and you're talking about half-lives and your half-life time period is longer, it's going to take a lot longer for that time to decay. Okay, so if I throw a bunch of radioactive material in a landfill and one takes 4 years to take the half-life and the other one takes 40 years to start to decay to his half-life, obviously the 40-year one is going to take a lot longer to decay. Okay, so that kind of answers 12 and 14. Generally, when you extend that half-life time, it will take a lot longer for it to decay.